Okay, so welcome to Chapter 5, Section 2. We are continuing with Calorimetry in Lecture 20, Part 2. Okay. And now we're going to talk about bomb calorimeters. They are nowhere near as exciting as they sound, because all they are is a fancy kind of calorimeter. Or I should say a specific kind of calorimeter. Okay. So here we have a tank full of water. Here's our thermometer. And here is a stirrer. That is to say, it is a device for stirring the water to make sure that heat is evenly distributed throughout the calorimeter. This here is the reaction vessel, because not all reactions can take place in water. And these two things sticking out of it are wires. The wires are used to ignite whatever it is you're going to burn in there. Now, the reason it's called a bomb calorimeter is because it is completely closed, okay? Or constant volume rather than constant pressure. And if you have something burning inside of something that's constant volume, a steel canister, what you've made is a bomb. Okay. Now, these things don't explode. They are designed so as not to do that. Not only are they big and heavy and made, like I said, of steel, but they only burn very small amounts of things in there. But, we like fancy names. We like pretending we're hardcore, even when we're not. Now, the math for a bomb calorimeter is very similar. Okay, so Q of the system is equal to negative Q of the calorimeter is equal to negative Ccal delta T. Okay. Notice that there's no math. Okay. And this is not a specific heat capacity. It is just a heat capacity. Okay. Because these things are very carefully calibrated, they put in a very specific amount of water, and then they rely on that to handle most of the work for them. They don't have to do quite as much math. So it's just a heat capacity, has a units of joules per Kelvin or joules per degree Celsius. It's just however much the temperature changes for the calorimeter, that's how much energy was released by the reaction. It works quite well. And thus, whatever the temperature changes, how much energy was released. You don't have to do too much work there. And these are the calorimeters that they use when they're determining the calories released by your food, or stored in your food, I should say. They just put a small sample of the food inside the reaction vessel down here, and then they burn it. And however much heat it releases is however much energy stored in the food. Rather straightforward. Or at least that's how they used to do it. I don't know if that's how the FDA still does it, or still requires it to be done. But bomb calorimeters, they're still around. They are not the most sophisticated calorimeters out there, but they are still out there. They are a good tool, they're solid, they're reliable. Okay. And the math isn't that much different. So let's say we have a calorimeter with a calorimeter constant. Ccal is equal to 5.50 kilojoules per degree Celsius. You burn a thing in there, it causes the temperature to change by 15.00 degrees Celsius. How much energy was released by the stuff? Okay. So Q of your reaction is equal to negative Q of the calorimeter is equal to negative 5.50 kilojoules per degree Celsius times 15 degrees Celsius is equal to negative 82.5 kilojoules. So whatever was in there, it released 82,500 joules of heat. Okay, this is, should be, hopefully, a little bit straightforward for you by now. Now, let's talk about something that's not quite so straightforward. Let's talk about inefficient calorimeters. Okay. So let's say you have a calorimeter that loses a bit of heat to the outside of the calorimeter. I mean, normally, when you're working with the calorimeter, you know that Q of your reaction equals negative Q of the calorimeter. And you just sort of make that assumption, that the calorimeter is a really good insulator, that all of the heat being lost by the reaction is gained by the calorimeter, or vice versa. All the heat gained by the system is lost from, or is taken from the calorimeter. But that assumption only works if there's no heat exchanged between the calorimeter and the rest of the universe. Okay? So how would you set it up in order to make that good? How would you take into account the heat that has been lost? Okay? So what you have is you have your heat of your, let's stop calling it a reaction. Let's go ahead and call it your system, plus the heat of the calorimeter, plus the heat that is lost to the surroundings, should all add up to 0. Okay. Now, for a perfect calorimeter, this is a perfect calorimeter, that would be 0. And then this would just be equal to negative Q of the system for a perfect calorimeter. Okay. And thus, Q of the system minus Q of the system plus 0 heat lost is equal to 0. Okay. So that's the perfect setup. But what about a more realistic setup? What's it going to be? Well, what that means is that the heat loss of the system is going to go into the calorimeter, and some is going to be lost to the outside of the calorimeter. And thus, Q of your system, whether that's a reaction or whatever, is equal to negative of Q of the calorimeter plus Q lost to the surroundings. And every calorimeter is going to have a little bit of heat lost to the surroundings. That's really unavoidable. So what you do is you calibrate your calorimeter. Okay? You find out how much heat is lost to the surroundings. And the way that works is that Q lost is equal to C cal delta T. It looks very similar to the bomb calorimeter, but it is different in that we're talking about heat being lost to the surroundings rather than heat going into a very carefully calibrated calorimeter where you don't care about mass. Okay? So, for example, say you have a regular coffee cup calorimeter, you can just drop in, something hot, hot metal, and thanks to, Q of the metal is equal to negative Q of the water, and you can solve for the final temperature. It's big stuff over little stuff, right? You know what the final temperature should be, but instead it's going to end up at a lower temperature because it's losing heat to the surroundings. So instead, it's Q of the metal is equal to negative Q of the water plus Q lost. Okay? So you can calibrate your calorimeter in that way. And so this is a calorimeter constant that tells you how much heat is lost, joules, for every degree Celsius change the calorimeter sees. A greater temperature change in any direction is going to see a greater response to the outside of the calorimeter. Okay? If the calorimeter is trying to gain, or if the water, I should say, inside the calorimeter is trying to gain a large quantity of heat, then it's going to lose more heat to the air around it. And if it's trying to put a lot of heat into whatever your reaction is, then it's going to gain more heat from the air around it. We will be seeing this in lab, and it's not particularly hard. I mean, we have this equation. I've already shown it to you. The equation itself, the algebra to get to it, they look nasty. It's not actually that bad. The real, I mean, and this is a very simple experimental setup, just dropping a hot thing into a cold thing, or you could just mix hot and cold water, and you know where they should end up. I mean, it's really a very simple calibration to do. You just put a hot thing and a cold thing together, you measure the temperature change, and you compare it to what it should have been. It's not the easiest thing in the world, but it's you know, it's not the hardest thing. Let's leave it at that. It's not the hardest thing. No, the hardest thing is understanding love. Okay. In any event, that finishes lecture 20. So, hooray! We can go ahead and end that lecture here. I'll see you next time in lecture 21.